Hi there, Mr. Sutton bringing you the IM3 Honors 7-6 homework solutions on conditional probability with tree diagrams. For number 1, we have John driving to school and passing 3 stoplights. We want a tree diagram to show the possible outcomes. So assuming he has an equal chance of getting a green light or a red light, here are our possibilities. So we have one branch where he gets a green light and another branch where he gets a red light. And again, let's assume that we have 1/2 chance of each of these happening. So he comes to the next light, and he has, again, half a chance of green, half a probability of red. And then down here, same deal, 1/2 green, 1/2 red. And oh, wait, John gets to a third stoplight. Well, there's a 1/2 chance that that light is green versus red, and the same thing for all of these other branches. So at the very end of this, what's the probability that he went green, green, green? Well, that's 1/2 times 1/2 times 1/2, which is 1/8. And all of these other leaves have the same probability, so this is 1/8 all the way down. And just as a quick check, if you add up these 8/8, that does indeed come out to a probability of 1. For number 2, we're talking about Lyme disease. It's estimated in this problem that 4% of people who spend time in the woods will get Lyme disease, and of the people with Lyme disease, the test to determine if you have it will give a positive reading 97% of the time. Of the people who do not have Lyme disease, the same test gives a negative reading 92% of the time. So these tests aren't perfect, but it looks like they're fairly accurate. So we want to make a tree diagram for this problem, and then there's a few other questions we'll answer after this piece of it. So our top level of our tree diagram, we need to look at where we have information about the whole population. The information we have about the whole population is whether or not you have Lyme disease. It's estimated 4% of people will get Lyme disease, so that means 96% of people won't. So our first branch, we're going to have disease is 0.04. That's the 4% who got it. And that means that then no disease will be 0.96. Okay, so the next branch here is whether or not the test gives you a positive or a negative reading. So if you have the disease, it says the test will give you a positive reading 97% of the time. So given that you have the disease, we would say we get a positive reading 0.97% of the time, or that this is already a percent. That means that the same test will give you a negative reading if you have Lyme disease, 0.03 of the time. And now if you don't have the disease, they said you get a negative reading 92% of the time. So that means you would get a positive reading for no disease 8% of the time. And then negative again, that's going to be 0.92. Now, in order to answer the questions, it'll be helpful if we have these leaves filled in, and we're supposed to do that anyway. So let's figure out if we multiply 0.04 times 0.97, the probability that you have the disease and you get a positive reading. Calculator for that. And it looks like that gives us a 0.0388. And let's see here. I'll just round. I won't even bother rounding it. Let's just keep it for now. And then let's keep going. So now we need disease and negative reading. So that's actually, let me just go back up here and steal my input. So 0.04 times 0.03, which comes out to 0012. And let's just do the rest of these real quick. So we got 0.96 times 0.8 is 0.0768, and now for this last branch, 0.96 times 0.92, which gives us 0.8832. So there was that piece, another leaf, and now we can go on to answer the rest of the questions. For part A on this question, we want the probability that a person gets a positive reading. So this positive reading is kind of bound up in 2 different branches here. We have disease and positive and no disease and positive. So we're just going to add those compound probabilities together, the 0.0388 and the 0.0768, and we'll use the calculator for this. So that adds up to 0.1156. So there's your probability, the exact probability. I mean, we could round it off if we wanted, that you have a positive reading, regardless of whether or not you actually have the disease. For part B, we want the probability that a person gets a negative reading. So we're going to add up the leaves on these 2 negative branches here. So 0.00112 plus 0.8832. And I can do this without a calculator. This is going to be 0.8844, I hope. Yep, we got it. For part C, we want the probability that if a person gets a positive reading, he has Lyme. So this is basically asking for the probability of Lyme given positive reading. So we need to take the probability that you got a positive reading and got Lyme disease and divide it by just the probability that you got a positive reading. So positive and disease, that was 0.0388, and we're dividing that by all the positive leaves. So 0.0388 plus 0.0768. So the denominator is the probability that you got a positive reading, and we're dividing that into the probability that you have a positive reading and the disease. Calculator time now. Dividing all of that out, I'm getting about 0.336 if we round it off, or 5.6, depending on how far you want to go. For part D, we want the probability that if a person gets a positive reading, he doesn't have Lyme. So now we're looking for no disease positive. This one right here, 0.0768, and we're still dividing that by the probability that you got a positive reading. So we still have the same denominator as last time around, but now we're dividing 0.0768 by all of this instead of dividing 0.0388 like we did in part C. So dividing this into the calculator now. And again, all that's changing here is my numerator. Still the same group that we're dividing things out of, though. So this comes out to 0.6644. For part E, we're asking the probability that if a person gets a negative reading, he doesn't have Lyme. So our branch that we're looking at here, we're looking for the negatives and we're looking for the no disease branch of that. So that's this group here, this 0.8832. But we're given that we got a negative reading to begin with. So we need to divide this 0.8832 by all the people who got negative readings, including these people up here who actually have the disease and still got a negative reading. So we're doing 0.8832 divided by this number plus this number up here. And calculator for this, doing that division out, we end up with 0.9986. So that's a pretty high percentage. That's your probability that if you get a negative reading, you don't have the disease. There's a pretty good chance you don't have it. It's not perfect, though. For part F, we want the probability that if you got a negative reading, you do actually have the disease. So here's disease and negative. That's this 0.00112 out here. And we're going to divide that by all the negative readings. So the 0.00112 plus this negative no disease part, 0.8832. This is pretty much like part E, only now we're doing 0.00112 up here instead of the 0.8832. So let's go to the calculator for this. So I actually just kind of cheated and grabbed my input from part E and replaced the 0.8832 with a 0.00112. Denominator is still the same, and now we get about 0.0014. So we have like less than a 1% chance actually that we have the disease if we get a negative reading. For number 3, we have a VCR manufacturer getting 70% of its parts from one factory and the rest from another. 3% of the parts from the first factory are defective. 2% of the parts from the other factory are defective. We want a tree diagram and some questions answered based off this information. So making our tree diagram, we've got 2 questions. Which factory and defective or good are kind of our 2 questions here. Which question comes first? Well, they gave us information about the whole population in terms of which factory it was coming from. They said we received 70% from factory A and the rest from factory B. So that's our first branch in our tree diagram because that's what we know about the population as a whole. So we can have a branch for factory A of 0.7 for 70%, and then factory B will have a 0.3 branch going that way. Now after that, the question is it defective or good? So for factory A, 3% of those parts were defective. That means we have a 0.97 that are good and a 0.03 that are defective. Now down here for factory B, it's going to be 0.98 versus 0.02 because only 2% of those parts were defective. So good will be 0.98, defective 0.02. And now in order to answer the questions, we're going to have to get all the leaves at the end of these branches. So for that, we'll just go to the calculator. And I'll just do these all at once on the calculator and then put them in here. So we had 0.7 times 0.97, and then we have 0.7 times 0.03. So those are our two leaves for the first big branch here. Now we have 0.3. I'll just grab this input. So 0.3 times 0.98. So there's our third leaf, and now we'll just do that again, but by 0.02. So there's our last leaf. So we had 0.679, 0.021, 294, and 0.006. For part A, we want the probability that a received part is defective. So these defective things are tied up in a few different branches here. We have the factory A parts that were defective, so that's 0.021 of the whole population. And we have the factory B parts that were defective, which is 0.006 of the whole population. We just have to add those two defective leaves together, which I can actually do without a calculator. That's going to be 0.027. For part B, we're asking if a randomly chosen part is defective, so we're given that it's defective, what's the probability it came from A? From B. So to answer the first part of this, from factory A, we have to take the factory A parts that were defective, which was this 0.021, and divide it by all the defective parts. So that was that 0.027 that we just found in the last part. So this is probability that it came from A given that it's defective. So 0.021 divided by 0.027. And we'll do that on the calculator. And it looks like that's going to come out to 0.778 if we round off. So there's a pretty good chance that if it's defective, it came from factory A. Now for factory B, we're going to do essentially the same thing, but we're just going to divide the factory B part here, 0.006, by the 0.027. So going back to the calculator, I'm going to grab my input from the first part of this problem, and now we're going to do 006, sounds like a secret agent, over 0.027. Comes out to 0.222 if we round that off. And these should add up to 1 because this was all the defective pieces that came from A. This was all the defective pieces from B, and we were already given that it was defective. So our total pool here was the defective parts. For number 4, we have an airline offering discounted tickets to customers who buy early, so more than 30 days ahead of time, and the company's noticed that 60% of its customers take advantage of these early bird fares. 25% do the regular fares, and 15% are last minute, less than 48 hours before the flight. They've also figured out that the no-show rate for the early birders is 30%, which is pretty high. But then again, you're buying these tickets way in advance, so a lot can happen, more than a month out. And only 8% of the regular fare customers are no-shows, and then 2% of the last-minute ones. I mean, really, who buys a last-minute ticket and then doesn't show up for the plane? Maybe if you overslept, I guess. So we want a tree diagram of this situation, and we're going to use that to answer a few questions after. So the first branch here, you taking the information we have about the whole population, that's going to be what type of tickets we're buying. So we've got 60% for early bird, so that's 0.6 for the early bird branch. Regular branch is going to be 0.25, and then we have the last 0.15 for the last minute customers. Now, after you've purchased one of these types of tickets, they have information about who shows up and who doesn't. So we have a 30% no-show rate for the early birders. That means that 0.7 of them are actually going to show up, and again, 0.3 don't show up. For the regular fare, they said that the no-show rate was 8%. So that means 0.92 of them show up and 0.08 don't. And then for last minute, it was 2% for no-shows, so 0.98 show up and 0.02 don't. And now to answer the questions, and just because it's a good idea and it's part of the problem, we're going to figure out these 8 different leaves here by multiplying each probability on each branch. So let's go to the calculator for that. Although actually, a few of these I can do without the calculator. So 0.6 times 0.7, that's 0.42. And then 0.6 times 0.3, that's going to be 0.18. And that should add up to 0.6, and it does. Down here now, I'm going to use the calculator for this one. we've got 0.25 times 0.92. That's 0.23. And then we've got 0.8. So that comes out to 0.02. And I miscounted. There's actually only 6 leaves, not 8 here, which, hey, that's less work to do, right? And this last one now, we have 0.15 times 0.98. So back to the calculator. I'm just going to reinsert some numbers here. So we got 1.5 instead of 2.5, and now 9.8 instead of 0.8. That's going to be 0.147, and then do the other leaf while I'm here. 0.2, that's going to be 0.003. So there are our last 2 leaves. For part A now, they want the probability of being a no-show overall. So we have to basically take all these no-show pieces of the population and add them together off of these different leaves. We have the no-shows from the early birders, that's 0.18, plus the regular no-shows, 0.02, plus the last-minute no-shows, very small, 0.003, whatever that adds up to. So let's see, these two are going to add up to 0.2 with another 0.003. We've got 0.203 for the no-shows. For part B, what's the probability of being a no-show and a last-minute customer? So this one, we're asking the probability of being both of these at the same time. This is not conditional probability. This is just straight up, we meet both of these conditions. So that's going to be, let's see, no-show and last minute. That's this branch right here, this leaf right here, 0.003. For part C, they want the probability of a no-show being an early bird customer. So this is a little bit different than asking what's the probability of being a no-show and an early bird customer. If they were asking for no-show and early bird, they'd just be asking for this 0.18 right here. But we're already being given the fact that we're just looking at the no-shows. So out of all the no-shows and only the no-shows, what are the chances that this randomly selected no-show is an early bird? So we need to take the 0.18, and now we're going to divide it by the chances that you're a no-show. So that's going to be that 0.203 that we found in part A. Or you could get that again by adding 0.18, 0.02, and 0.003. So plugging this in the calculator now. That's going to give us about 0.887. There we go. So there's an 88.7% chance that a no-show turns out to be an early bird customer.